discrete signal processing and noise in the system. So was introduced to thermocouple scanning devices early on in life. And what this means is there's, for conversation's sake, 8 thermocouples out on a process somewhere. They're on a tower, bottom to top. So you know where those thermocouples are. Those are temperature measurement devices, watching the external skin temperature of that tower. So you've got 8 thermocouple devices from the bottom to the top. How do you account for, how do you measure those? How do you put them into the computer? Well, you use an analog to digital converter. You add some sophisticated circuitry to make this resistive thermocouple device work. And you use read relays. So you can sample each thermocouple in sequence, connect it to that analog to digital conversion system, make a computer number into it, and go off and computer it, artificial intelligence it, right? So you've taken an analog signal, and one channel at a time you're going to sample each channel, then you're going to write to memory, then you're going to come back and sample the channel again. And through this, there's that read relay I happened to mention. So you have a few hundred of these boards. Each board has 8 of these little read relays on them. One of the challenges in these read relays is their life cycle, their lifetime, their lifespan. It's a industrially rated statistic within that device's physical characteristics you should get from the manufacturer. But the characteristic of the failure of the read relay, there's really 2 failure modes. One is it breaks, welds closed or welds open. Let's call that a break. So there's a fails open or it fails closed. 2 absolutes, right? But there's a third mode. There's a third mode where the actual bimetallic device in that read relay, this tiny little read relay that's just going like this when it's told to. Well, it does this. It bounces or it... So now, that single A to D on the back side of this thing that's doing the counting is seeing the channel the computer enabled. So it's scanning channel 1, channel 2, channel 3. But all this time, channel 6's read relay is bad and bouncing and putting a little signal on there. So now you have 8 thermocouple devices not reading correctly. Not just one, you have 8. So you notice the issue. You replace the board and life goes on. You tag it, send it off to a vendor or repair it in-house. Either way, take a note, make a note. And that failure happens a couple of times over some months. And you go back and look at how often does that read relay flex. The engineering statistics on that read relay flexing say it's got 10 million cycles. Well, you're polling that maybe 10 times a second. Depends on your scan rate that are set up in I/O tables for this software that you've engineered before spreadsheets were invented. Oh my gosh. So there's hopefully kind of a walkthrough of troubleshooting the idiosyncrasies of binary analysis. Like I said, I just talked through a case of where it's either on or it's off, but then it can chatter. This is the same odds of a nickel landing on edge, 1 in 6,000. So what you do as an engineer is you look at your boards and your components and how many are out there, and you initiate a life cycle study to make recommendations for the repair shops that might repair your electronics, or your in-house technician. So you build up these rules that maybe it's a good idea every time they see one of these boards to replace all the read relays and date them. And this can go back too, even to manufacturing, identifying bad manufacturing runs, because some of this stuff is tracked that much. So there's too much on a bad read relay. Piece of this as well is I just introduced a third state, off, on, and noisy. That third state is a discrete noise inside a discrete signal, and yet it can confuse other signals. Did that help?